So in this section, we will be studying the working principle of fiber optic system in detail. So to understand the working principle of fiber optic system, we need to draw a few simple ray diagrams to understand how the ray of light behaves during refraction depending upon the medium through which it is passing. Whenever a ray is passing from rarer to denser medium, obviously because of the change of the refractive index of the medium, refraction happens. So let me name it as N1. Refractive index of rarer medium is N1 and denser medium is N2. So here we know that N1 is less than N2. So under such circumstances, when the ray of light is passing like this, it is a point of incidence, and this is a normal n, say n dash. Now usually this is a undeviated direction of motion of the ray of light, isn't it? Now since we have that there is a change in the medium, it has entered, this particular layer is the interface between two medium. All right, since there is a change in the medium, what will happen? The ray of light will move towards the normal drawn at the point of incidence. So instead of going directly, the ray will be going like this. So that means it has shifted towards the normal. So this happens when the ray of light is traveling from rarer to denser medium. It moves towards or shifts towards the normal drawn at the point of incidence. So this is the point of incidence. Now this is what we know for ray of light traveling from rarer to denser medium. Under such condition, from Snell's law, we know that sine theta I, if I call it to be theta I, and this will be our theta R. Theta I is the angle of incidence, theta R is the angle of refraction. So sine theta I by sine theta R is equal to N2 by N1. Here N1 is less than N2. This is what we know. Here again I would like to mention that theta is the I is the angle of incidence and theta R is the angle of refraction. Alright, O is the point of incidence, N dash, this is our N, this is our N dash, is the normal drawn at the point of incidence. So this is a situation for rarer to denser medium transition. Next is, if it is the opposite, say you have a interface and this is your denser medium and this is your rarer medium. This is N1, this is N2, and this time N1 is greater than N2. And under that situation, so this is the normal drawn at the point of incidence. So if you have an incoming ray of light incident at O, then this is supposed to be the undeviated ray of light, isn't it? But since it is moving from denser to rarer medium, what will happen? The refracted ray will shift away from the normal drawn at the point of incidence. So here you can see that it is going away. Now in this case, this is our theta I and this is our theta R. So again, using the Snell's law, what we can write? Snell's law of refraction, again we can write that sine theta I by sine theta r is equal to n2 by n1. Now let us study a special case. We have an interface. This is our rare medium. So here we have, this is a special case. So again we have a normal drawn at the point of incidence. This is again n1, n2, n1 greater than n2. Now if the ray of light is incident at an angle, at a special angle, so this is our theta I and this is a special angle. Why special? Because if the ray of light is incident at such an angle and this is a undeviated ray of light, it should have traveled without deviating if there is no change of medium. But for a special angle called critical angle, what happens? The ray of light moves like this. So in this case the angle of refraction becomes 90 degrees. So what we have got, theta, if theta I is equal to theta C, theta R becomes 90 degree. So again applying the Snell's law, what we have, sine theta I by sine theta R is equal to n2 by n1, that we have already. But in case of sine theta I will write theta C. Theta C stands for critical angle. Theta C stands for critical angle. Now, and in place of theta R it is 90 degree and this is n2 by n1. And all of us know that sine 90 degree is 1. So it is sine theta C by 1 is equal to n2 by n1. So it is simply sine theta C is equal to n2 by n1. And therefore we have theta C is equal to sine inverse n2 by n1. So this is a special case when the ray of light is moving from denser to rarer medium. Now in another case, there is a fourth case we are studying. Similar situation. This is the denser medium. This is the rarer medium. This is n1. This is n2. n1 is greater than n2. Now in this particular case, now if the ray of light is incident at an angle theta I, which is greater than theta C, then what happens? This ray of light, instead of traveling towards a rarer medium, it will return back to the same medium from which it was traveling. So this particular phenomenon, so here this is our theta R. It went back. So this is called total internal reflection. This phenomenon is called total internal reflection. That means when the angle of incidence while traveling from denser to rarer medium, if the angle of incidence becomes greater than the critical angle, then the ray of light, instead of traveling to the rarer medium, will return back, will bounce back, will reflect back to the original medium, that means the denser medium. This phenomenon is called total internal reflection, and this particular phenomenon is very, very important in the field of communication because the optical fiber that we were discussing, that it works by using light waves as a messenger, can do it because of this particular principle. So the working principle of optical fiber system is the total internal reflection. In the previous section I have discussed the structure of the optical fiber. So it looks like this is the core, and then we had a cladding, right? So in the transmission of the information, basically the core and the cladding plays the most important role. This is the core and this is the cladding. Let me name that. In the refractive index of the core is say N1 and refractive index of the cladding is say N2. Now we need to decide which one should be higher refractive index, which one should be lower refractive index. Now for that, let us draw a diagram. Say this is the core. I am drawing only the half cross section. Say this is the cladding, outer jacket, and let us assume that this is the axis of the optical fiber, and the region inside the blue line is the core. So this is our core, and what is the refractive index of the core is N1, and this is our cladding, and refractive index is N2. Now what happens, say ray of light will enter here. It can enter like this, 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 in any direction. But mostly the rays of light which are passing through the core will actually pass the information. Okay, so now we all the rays of light which are coming with some information entering the core will not be successful in transmitting the information. Thing is, ray of light incident at a certain angle only can contribute in passing the information, because only those rays of light whose enters this core and suffers total internal reflection will be successfully passing the information to the other end. But those rays of light who do not fulfill the condition for total internal reflection will simply pass out of the core cladding surface. So how these conditions are fulfilled, let us get a view of that. This particular area is the air core interface, right? Now say a ray of light is incident at the air core interface. So since it is moving from rarer to denser medium, obviously it will move, and this is our normal drawn at the point of incident. So obviously it will move towards the normal, and it will then fall on another interface, that is between core and cladding. So first refraction happens at the air core interface, another refraction happens at the core cladding interface. Okay, at the core cladding interface, theta c is sine inverse theta n2 by n1. Okay, now say here this is the angle of incident, this is the angle of refraction. Now it is incident here again, so this is another point of incidence. Now this is our theta I, alright, and if the ray of light has to contribute in passing the information, it has to bounce back. That means there must be total internal reflection. Now for total internal reflection to happen, N1 must be greater than N2, because total internal reflection happens only when the ray of light is moving from denser to rarer media. So that means here it is very much clear that if the light has to pass through the core of the optical fiber to transmit the information, it must suffer total internal reflection at every core cladding surface. And for that to happen, core must be denser than the cladding. Again, when it is a denser to rarer medium transmission, another condition that has to be fulfilled, that this theta I must be greater than theta c. So there are two conditions. One is core must be denser than cladding, and second is theta I must be greater than theta c. and then only we can ensure that the ray of light is suffering total internal reflection, and that ray can only pass through the core, that will be trapped inside the core of the optical fiber for good, and it will be successfully transmitting the information from sender to receiver. This is one condition. But if any ray of light is incident at any another angle, okay, which doesn't fulfill this particular condition, that ray of light will pass out of the core cladding surface and move into the air. Okay, so that means all the rays of light which are falling here are not successful in transmitting the information. So it is very much okay to say that around this axis of the core there is a cone, imaginary cone. If a ray of light is incident within this cone at the air core interface, this is the air core interface, this area is the air core interface, then the rays of light moving inside the core will definitely go through total internal reflection. But if any ray of light is incident outside this particular cone, then it will be a failure. It will not go through total internal reflection. It will not be able to pass the information from one end to another end, because it will not satisfy those conditions for total internal reflection. So this particular angle is called, so if I consider this to be the axis, core axis, so this particular angle of this cone, say alpha, this angle is called acceptance angle. So if the ray of light enters through within the acceptance angle, total internal reflection happens and light rays get trapped for good. But if any ray of light falls outside this acceptance angle on the air core interface, then that ray of light, total internal reflection doesn't happen and light will simply escape out of this surface. So summarizing, so for proper transmission through an optical fiber, light must enter within the acceptance angle. So light entering the fiber within this particular angular range will definitely undergo total internal reflection and travel down the fiber. And obviously for that to happen, cladding must be less denser than the core, and it must satisfy the and only if it enters through this entering through this particular angle ensures fulfilling of the condition theta I greater than theta c, where theta c is sine inverse the ratio of the refractive index of cladding and refractive index of core. That's all for the working principle of an optical fiber system. Thank you.